welcome everyone to today's seminar. The speaker today is Taye Demissie, and the title is Synergy between Experimental and Computational Approaches, Photocatalytic Double CH Functionalization. So with that, I'll give the stage to you, Taye, and remember, this is the microphone, so try to speak in that general direction. Okay, you're welcome.
Okay, thank you. So I will not repeat the title of my presentation. Already Magnus has introduced it, and I will talk about some introductory concepts about the project and some computational studies, followed by experimental observation, and using computational and experimental techniques. We propose also the reaction mechanisms, and I will end the talk using some concluding remarks. So starting with some basic background concepts, I will start with CH functionalization. It is a type of reaction in which carbon-hydrogen bond is cleaved or changed to carbon-carbon or carbon-nitrogen or carbon-oxygen bonds. For example, in this study, they used benzene reacting with styrene in these reaction conditions, and then making a new carbon-carbon bond and forming diphenyl-ethene in this case. And in another example, if we take indole, this one, and this biologically active organic compound, in these reaction conditions, copper catalyzed reaction condition, and making a new carbon-carbon bond. By this carbon-carbon bond will be formed, and then a new functionalized or diversified organic compound or biologically active compound can be obtained. So CH functionalization is a powerful technique for organic chemists or medicinal chemists in order to synthesize target-oriented compounds or diversity-oriented compounds. So in the case of the target-oriented synthesis, for example, they take different compounds or different substrates, and they are only one compound like this one. In the case of the diversity-oriented synthesis, they start from a single compound or single molecule, and then they start to make different compounds out of this one. For example, in this case, we have one compound here, and then synthesizing three different compounds, again re-diversifying the three compounds formed in the first step, and then getting all these kind of compounds. So in this case, we have a diverse or different kind of structures, and in this case, we can synthesize only one compound from different one. So CH functionalization is very, very important for this kind of organic and medicinal chemistry fields. And there are two ways, at least the common ones, of CH functionalization, and the first one is the via CH activation, and this is the most commonly used type of CH functionalization. It creates an organometallic complex, like this one, for example. If we take this example, we take this transition metal complex, and then reacting with some organic compound, after releasing nitrogen, it forms a new transition metal complex, this one. And this transition metal complex can activate the CH bond, like this one, by forming a transition state structure or transition state complex. And after undergoing consecutive reactions, then we can have the newly diversified or functionalized organic compound like this one. And the second type of or way of CH functionalization is photocatalysis. In photocatalysis, mainly, as its name also implies, light is absorbed by the catalyst, and then that catalyst gives or accepts electron from certain kind of substrate or radical source, and it forms a free radical. And the free radicals can undergo radical addition reactions. For example, this one, this chemical reaction, we have a ruthenium-2 complex, and this ruthenium complex absorbs light and gets excited, and this excited ruthenium complex can accept electron from an electron donor like this one, and it reduces to ruthenium-1. Then this ruthenium-1 complex is ready then to give its electron to, for example, this trifluoroiodomethane. And then after accepting electron, the trifluoroiodomethane will start to break the CI bond in order to form the CF3 radical and regenerating the ruthenium-2 photocatalyst. Once we have this free radical, the CF3 free radical, it can easily react with boronic acid, and it forms a newly functionalized aromatic compound like this one. So we have this mainly or commonly used type of CH functionalizations. So this is not my focus of talk today, and I will only focus on the photocatalysis part. So photocatalysis is it's a kind of reaction that uses a catalyst or a photocatalyst in order to accelerate the given type of chemical reaction. If we take this example, iridium complex, then the iridium complex, as I told you in the previous slide, absorbs light, like this one. For example, in our case, we have a blue light emitting diode, and then it excites in these cases. And this excited iridium complex or the photocatalyst have two options, or it has two fates. The first one is it can give its electron to an electron acceptor like this one, and it forms these two kind of species, both singlet. And the other one is it can also accept electron from an electron donor, and it again forms this kind of states. And this one we call it oxidative step, and this one is we call it reductive step. And after exciting and transferring electron with the electron acceptor or with electron donor, then the photocatalyst can have these two processes. The first one is just exciting and negating the singlet excited state, and through intersystem crossing it converts to triplet excited state, and the photochemistry then starts to take place from the triplet excited state. If we take again a ruthenium-2 catalyst, and if we see the general steps or the general process of photocatalysis, we have the ruthenium-2 and absorbing light, and it excites to ruthenium-2 again, and this ruthenium-2 will have either it can undergo a reductive quenching cycle or it can undergo the oxidative quenching cycle. In the reductive quenching cycle case, it accepts, it donates electron to the electron acceptor, and it accepts electron from electron donor, and it converts to ruthenium-1. And this ruthenium-1 again gives its electron to an electron acceptor and comes back to ruthenium-2, and this one, or the species that accepted the electron, then can generate the free radical. In the oxidative quenching cycle, the ruthenium-2, the activated ruthenium-2 photocatalyst will give electron or donate electron to electron acceptor and change or oxidizes to ruthenium-3. Again, this ruthenium-3 will accept electron from an electron donor of this kind and regenerate the ruthenium-2. And the donor will have one extra electron, and then it can generate the free radical, which will go radical addition reaction for the photochemistry. Application examples, how photocatalysis is applied, and in this study, in this 2012 study, they used trifluoroiodomethane to react with some kind of boronic acid in order to form these functionalized aryl compounds or aromatic compounds with very decent yields. And they also proposed the mechanism for this chemical reaction. What they proposed is ruthenium-2 absorbs light and forms this activated or excited ruthenium photocatalyst. The ruthenium-2 catalyst then accepts electron from this copper complex, forms the copper on the ruthenium-1. Ruthenium-1 can then give one electron to the trifluoroiodobutane in this case, and forms this CF3 radical. Then CF3 radical reacts with the boronic acid in order to form the new compounds of this kind. And another example is the conversion of the NO bonds to NC bonds in these reaction conditions. Both are photocatalytic reactions taking place at room temperature mostly, and they got very decent yields again for this kind of diverse organic compounds. And they proposed also the reaction mechanism for this iridium-1, a bit different from that of the ruthenium catalyzed reaction. So we have iridium-3 absorbing light, and it excites to iridium-3 excited state. And this iridium-3 or activated iridium-3 can transfer electron to this compound or compound 1. And the compound 1 can then break this NO bond after accepting one electron, because this bond or the NO bond will become very loose after accepting one electron. And it forms the conjugate base and this free radical, and this free radical can react with this kind of organic compounds, forming a radical intermediate product. And in this step, in the catalyst cycle, in this cycle, after giving one electron, the iridium-3 is converted to iridium-4. Then we have this the radical intermediate, and this radical intermediate can give electron or one electron to the iridium-4, and iridium-4 converts to iridium-3 or regenerating the catalyst. And it forms also this carbocation, then this carbocation can react or interact with this conjugate base. This conjugate base will abstract this hydrogen and neutralizing this carbon atom, and finally we have this new NC bond formed like this one. The third example I have is conversion of the nitrogen-hydrogen bond to carbon-nitrogen bond in these reaction conditions. This is internal cyclization reaction, and again the yields are also very nice yields they got. And the mechanism proposed for this reaction is this one. The base, a base will come to this compound, abstracting this hydrogen and forming this N-, and simultaneously ruthenium absorbs light and get excited, and this excited ruthenium to photocatalyst will transfer or accept one electron from this N- and convert to ruthenium-1. And after giving one electron to the ruthenium-2, this compound will generate this radical, and the radical attacks this carbon atom and forms this newly formed nitrogen to carbon bond. And after consecutive reactions, then it reaches to the final product. So this CH functionalization is very powerful because of this kind of application, because of its ability to form diversified organic compounds or drug-like molecules. And this leads to be used as a powerful tool for late-stage functionalization. And it's extremely useful toolbox for medicinal and organic materials chemistry. Then, if this is so, we can design some kind of chemical reaction using computational and experimental approaches. We can have some kind of photocatalytic reactions by just combining these two approaches. And if we are thinking about photocatalysis, then we need to think about also the way how the radicals are generated. And after generating the radicals, we also need to think about how the radical is going to attack the substrate. and at what position of the substrate the radical will attack. And after that, we need to think also how the reaction mechanism is looking like. And for this, we used both these two approaches, like experimental and computational techniques, and I will start to show you what we did in our group. So the first one is the radical generating step. Before going to anything, we have to identify what kind of radicals we will get. And in this example, what we used is this kind of compound as a radical source, methyl radical in both cases, and iridium complex. As I have showed you in the previous slides, iridium complex will absorb light, and after getting or change or converting to triplet excited state, it donates electron to the radical source, and after getting one electron from the photocatalyst, this bond will become very loose. And also this one, the oxygen-oxygen bond will become very loose, and the electron or the unpaired electron will be populated on this oxygen atom. And after that, we can easily break either this bond or we can break this bond in order to form the methyl radical. So we have two possibilities: breaking the carbon-carbon bond here, generating acetic acid and acetone as byproducts and getting the methyl radical. In the second case, we can break this carbon-carbon bond and generating carbon dioxide, the T-butanol, and methyl radical. After catalyzing this one, we visualized the spin density of this chemical reaction, and it looks like this one. The the iridium catalyst already started to transfer the electron to the radical source like this one. If we slightly or gradually separate the radical source from the photocatalyst after getting electron from the catalyst or from the iridium catalyst, the spin density completely populates on this oxygen atom, or the oxygen atom that is near or closer to the T-butyl group. And after having this unpaired electron on this oxygen atom, then you can easily break the carbon-carbon bond. And for this, or to see or to study this one, we calculated the potential energy surface for this kind of process. We have three cases. One is breaking the CC bond from this one, and second one is breaking the CC bond from this one, from this part, and the other one is for option one or from reaction one, but without any catalyst. So if we don't have the catalyst, or if the radical source is not getting an extra electron from the photocatalyst, then we cannot break the CC bond. So we forget about this chemical reaction, and we consider only these two options. So in the first case, or if I am breaking the CC bond from this part, we have an activation energy barrier of about 11 kilocalories per mole. And if we break this CC bond, we have an energy barrier of 35 kilocalories per mole. So it is very easy to notice that this is the reaction, or this is a process that is generating the methyl radical. And this is in perfect agreement with the experimental observation that is reported in 2014, in which they observed only acetic acid and acetone as the only byproducts in the reaction medium. So in this way, you can easily model the radical generating step. And to validate the process or the method, we also considered other radical sources. In this case, we used diethyl bromomalonate in order to generate a malonyl radical. So this one is the uncatalyzed one. You cannot break the CBr bond, and this one is for the catalyzed one. You can easily break the CBr bond and you can generate the malonyl radical and the Br minus or bromide. And the spin density visualization shows that spin unpaired electron density is populated on this carbon atom. And we have also another example for breaking Ci bond, carbon iodine bond, and that is proceeding to internal cyclization reaction to form a new compound. So it works. After generating the radical, then the next one is modeling the radical attack state. We took this methyl indole and we have generated in this PES we have generated the malonyl radical. Then malonyl radical reacts with this methyl indole and forms the newly malonated methyl indole. And for this we need to calculate the potential energy surface to see how the radical attack is looking like, and we got this kind of potential energy surface. So the malonyl radical is attacking this carbon atom, and it proceeds to some kind of transition state with a very low energy barrier, 5 kilocalories per mole, and then generates this radical intermediate product. And after some steps, it can proceed to the formation of the final malonated product. And using this PS calculation and other related calculations, we proposed the reaction mechanism for this reaction. What is going on is the ruthenium photocatalyst absorbs light, as I have explained it already in the previous slides, and then single electron transfer making ruthenium 1, and the ruthenium 1 will undergo single electron transfer to the bromo malonate, and then the bromo malonate will generate a malonyl radical like this one, and the malonyl radical attacks the 1-methyl indole, generating the radical intermediate, and radical intermediate will transfer its electron, this unpaired electron, to the base, and it generates this carbocation, and the carbocation is then ready to give its electron, its hydrogen to the Br minus. This Br minus is coming and abstracting this hydrogen and neutralizing this carbon atom and forming this C double bond like this one. So we have the monofunctionalized methyl indole we got from this step. And in the experiment, in the previous experiment, they got 82% of yield for this compound, and in our group we got 68% yield of this compound from this chemical reaction. And what we proposed is this is the one that is interfering or competing with this reaction mechanism or with this reaction, so that the yield of this compound is decreasing, or it's a bit lower from our expectation. Then after publishing these results in 2015, the experimentalists from our group came out with these results. The first one is they started to validate the previous study by Stephenson and his group reported in 2010. Methyl indole reacts with this bromo malonate in these reaction conditions and forms this monofunctionalized or monomalonated methyl indole with 82% yield at about 18 hours after 18 hours. So they started this one, and what they got is this one. The concentration of methyl indole is decreasing, and the concentration of this monofunctionalized methyl indole reaches to maximum at about 10 hours or after 10 hours. And after about 12 hours, the concentration of the malonate or the monofunctionalized methyl indole will start to... What they observed is a new kind of compound is appearing from the reaction medium like this one. So we have this as or in agreement with the previously reported results, but unlike the previous studies, a new compound has already started to be seen in the reaction medium, and this compound has two CH functionalized groups, CBr bond or newly formed CBr bond and newly formed CC bond. And the concentration of this new compound reaches to maximum after about 24 hours. and about 84% yield is obtained after 48 hours of reaction time. And in addition to this one, it's about 84% yield, and the other one, or the rest, is going to some kind of newly formed CC bonds. In this case too, we have a monofunctionalized and difunctionalized methyl indole. And the fourth one is this one. So we have two species. If I start from this one, we have this one, and second one, and third, and the fourth one. So this indicates that there are maybe two kind of reaction paths that is undergoing into the formation of these compounds. Most probably compound 2 can be formed from compound 1, and compound 4 can be formed from compound 3. And for this, they used the ultra-high performance liquid chromatography and control experiments to identify these two reaction pathways. So we have a reaction pathway 1 that is forming the monofunctionalized methyl indole at C2 position. And then this monofunctionalized methyl indole at C2 position will get brominated in some way and forms this compound 2 with 84% yield. And the second reaction, or reaction path B, is a formation of the malonation at C3 position for compound 3 with 4% very low yield. And compound 3 can convert to compound 4 or C2 malonation. And they also used controlled experiments to see how fast the two reactions are, and from their observation, it's seen that this reaction is very fast compared to the formation of compound 4. So if we have these 4 kind of newly formed species, then we can, or we should be able to see how the compounds are formed by calculating the reaction mechanism. So what we started is we have these two compounds, the methyl indole, the starting material, and we have this final compound, or the brominated one. Because in this step, as I showed you here, we have 84% yield, and it has CBr bond. And once we have this brominated compound, it's very easy in order to further functionalize it, because you can easily use the common ways of organic reactions, like, for example, the Grignard reaction. Then for that, we focused mainly for the brominated species. So I have already shown you this one in the previous slide. So we have this, methyl indole, reacting with the malonyl radical, forming this one with very low energy barrier, and then transferring electron to the base, forming the carbocation intermediate product. And the carbocation intermediate products will react with the bromide, and bromide will abstract this hydrogen, neutralizing this carbon atom, forming this compound 1. We are safe with this one. It's already published also in 2015 in our paper. And this is the new one that is the most interesting part of the study. So to convert compound 1 to compound 2, or to brominate this compound, we need these steps. We have bromine radical, and we have also bromide in the reaction medium. How the bromine radical is formed? We have the previous steps, and from the bromide reacts with the bromine radical, forms this Br2 minus radical. And Br2 minus radical is exergonic reaction. It can easily proceed to the formation of Br2 minus radical. And Br2 minus radical can give its electron to the ruthenium-3 that is formed in the reaction medium, and it forms bromine molecule. And then bromine molecule can easily react with this compound 1 with very low activation energy again, or energy barrier. and it forms compound 2 with a release of hydrogen bromide. Okay, then this is a bit difficult to understand, and it's also a bit confusing to see it how the to see how the reaction is going on, and for that we proposed controlled experiments to do. And the control experiments involve different experiments. The first one is using the synthesized or the extracted compounds independently of each other. Because in the previous controlled experiment from the ultra-high performance liquid chromatography study of the reaction progress, we have all of the 4 compounds all together. But in this one, we are doing the reaction independently of each other because the compounds are already extracted, and then using or making the reaction using these independent or individual compounds. So we have the monofunctionalized C2-malonated compound. This reaction condition, the bromine source is different. In the previous one we have the bromomalonate, but in this case we have the bromine salt. And then it forms 93% of this brominated compound and it works. So this is one indication that the reaction mechanism is in good agreement with the experiment. And second one is using this compound, the compound 3, same reaction condition like the photocatalysis one or the general reaction procedure, and it forms 29% of compound 4. So this indicates that this is performing in reaction path A, and this one is performing in reaction path B. And I will bring you back to this slide. We propose that Br2 is responsible for the bromination of compound 1 to compound 2. Because in this case we have Br minus, and there is no indication or any kind of information that is telling us that Br2 is operating in the reaction. So for that we used these reaction conditions. We took the compound 1, C2-malonated compound, then exposing to bromine and in these reaction conditions, and it works. In full conversion or complete conversion of 1 to 2 is taking place in this reaction condition. So this also indicates that this reaction is the one that is responsible for the conversion of compound 1 to compound 2. And other one is checking what kind of reaction is the best one, or what kind of reaction condition is optimum. And for that we did this kind of experiments. This is what we have. Methyl indole, bromomalonate, same reaction condition as before. Compound 1 will be formed plus compound 2. And this is what we have. We use different catalysts. The catalysts are mostly the most commonly used one, ruthenium and iridium photocatalysis. And the catalysts are just, they are good enough in order to have this kind of reaction. It works in all of the photocatalysts. And the other constraint we use is the base. The base plays a profound effect. In all the cases, this base performs much better than this one. In these 4 bases, base 9 to 12, there is no reaction observed, or there is no compound formation observed in the reaction medium. But in this case, we have more or less good yields, even though one is different from the other one. And for the base type, I mean for the solvent type, the dimethylformamide and the DCM are they are ideal solvents for this chemical reaction. It's well known that DMF is the best known solvent for the bromination of organic compounds. So this reaction condition, ruthenium photocatalyst, this base DMF is the optimum reaction condition for this kind of chemical reaction. So in this way, we discovered a novel photocatalytic double functionalization approach, and we proposed also a reaction mechanism based on DFT calculation and controlled experimental techniques or approach. And this is a new way of development of photocatalytic CH bromination, and it's an indication that it's a very good way of further functionalizing biologically active compounds, because as I told you in the previous slide, once you have this brominated compound, you can easily use the most commonly used ways of organic reaction like the Grignard reaction in order to further functionalize the compounds, mostly important for biologically active compounds. So it is a nice tool for diversification of this kind of biologically or active compound, or for drug diversification. So yeah, that is what we used, and yeah, we did it. And it's very interesting, and I would like to thank my supervisors, Kenneth and Jorn, and collaborator, PhD student Urna, for nice work, and thank you.
Thank you, Taye. We'll open for some questions. We'll start with Tromsø. And Bingao.
Yeah. Could you say more about your last point in the conclusion, the drug diversification? Could you give more clue or more hints? What does it mean? The last point.
This one.
Yeah. For drug diversification.
Yeah. Okay, I have 2 points. One is this one. Remember this one? We have this bromine here.
Yeah.
And I will take you back to the so we have this one. So you remember the compound 2 with bromine.
Yeah.
Then we have the, for example, do you know Grignard reaction? Yeah, they are using, for example, like magnesium catalysis, and then making a complex, then converting the CBr or C hydrogen bond to a newly CC bond. So if I have already the brominated compound 2, then I can use some kind of different functional groups or different compounds, other compounds, and then I can introduce these new compounds to the brominated compound 2, and then I can make different other compounds or indoors.
Okay. Can I understand in such a way that do you mean this can be a potential drug candidate for drug discovery, or?
No. The compound is not a potential candidate, but the method we discovered is the potential method for diversification of drugs.
Okay. Yeah, we can discuss later maybe.
Any more questions from Tromsø? If not, then we'll go ahead with the questions from Oslo. I think Einar, I see you.
I'm just curious to know the versatility of this method, and it seems to be very selective towards the hydrogens on the pyrrole ring rather than on the aromatic system. So, could you say anything about the selectivity and specificity and the scope? Can you extend the scope to other hydrogens, but these particular vulnerable ones? It seems to be a key point that you have the nitrogen around in order to activate these for these particular reactions. Could you comment upon that?
Yes, that is a very good question, and we did that, yeah. And in total, we tested about 60 molecules. So it works for most of the 60 molecules. And the organic compounds are different kinds, oxygen-containing heteroaromatic compounds, nitrogen, Yeah, a lot of different compounds we tested. Yeah, it works for other organic compounds. So it's not only because of the indole.
I didn't catch that.
And not only what the...
Because of the indole.
Yeah. So, but in your, it seems to be a selectivity when you compare the, there are other hydrogens on the ring, on the aromatic ring there, seem not to be attacked. So there seems to be some sort of, yeah.
Okay, yeah. That is right. And I'm not sure if you remember my last year talk, April 22, 2016, I had the same presentation. And in that presentation, I showed how site selectivity is taking place. Do you remember this one?
Slide number 16, right?
No problem, I can show you. I don't have it.
He can refresh your memory now, so...
Yeah, I can refresh it, yeah. What we did in that study is we used the molecular charges and QTAM charges in order to identify the carbon atom that is more susceptible for the radical attack. So we have a tool for that too.
Okay,
So it's very easy in order to identify the very active sites that the radical is going to attack.
Okay, just one thing on the second to last slide, you showed that this reaction basically doesn't work with any other bases at all, like slide 26. And I was wondering, is that just, I mean, I guess it's more than just acidity, right? What is it that just makes this only work with this one base and just not with all the others you tested?
Okay, good question. I will take you to this reaction mechanism, or I will start with the first reaction mechanism. I have two reaction mechanisms. One is for the mono and the other one is for the di. So this one is for the monofunctionalization. So we have a ruthenium, excited ruthenium catalyst. Then this ruthenium catalyst should change to ruthenium 1. And this is the reaction mechanism how ruthenium 2 is changing to ruthenium 1. Because the base will give or donate electron to ruthenium 2 and convert us to ruthenium 1. So we have the base. And in the second reaction mechanism, here, the base is giving electrons to the catalyst in the previous slide and forming this radical base or radical cation base. And the base is again, or this species is again responsible for accepting this electron for the formation or conversion of the radical intermediate product to the carbocation intermediate product. So we need this species to accept and donate electron. Donating electron to the photocatalyst and accepting electron from this radical intermediate. But in the other bases, we don't have that kind of possibilities. Maybe for pyridine, we haven't tested this one in the calculation. But this is the main reason that this base is performing very well for this reaction condition.
More questions from Oslo, or? Yeah.
Yes, go ahead, please.
I was wondering, how did you create the radical, the wave, the radical wave function? How did you unpair those electrons?
What do you mean?
So you just asked to the program that he must look for a doublet, a triplet, or something like that, or the program, the calculation just go to those states automatically?
No, it's doublet. I'm using doublet. For example, in this case, I'm using doublet. So charge is 0 in this case, and I have doublet. Charge is +1, singlet in this case, because one electron, unpaired electron, is already transferred to the base. I'm
when you
fixing the multiplicity by myself.
okay, and you said you use Mulliken charges. Charges or Mulliken spins?
No, in this study I have not used any charges because I don't need them. The Mulliken charges and the QTAM charges I mentioned is for the last year's talk.
Okay.
More questions from Oslo? Well, I have one. So, did you mention which software you're using for this? Is it Gaussian or?
Yeah, Gaussian.
Yeah. Okay. Okay. Thanks. So that was my question. Okay. So, I guess that was it, Magnus, or any more questions from
So
Tromsø?
if there are no more questions from Oslo and no more from Tromsø, then that is the end, and this is also the last talk before Easter. So I would like to wish you all a nice Easter and see you back after Easter.
Thank you.
A nice